All right, so let's now look at exercise 9. Most of the stuff you can get from the slides or from the lectures that I kind of expect you to watch, and from the movies and things like that. So let's go on down. So we don't really start till question 6 with anything that might be tricky. A sled and the musher have a combined mass of 250 kilograms. What is the normal force exerted on the sled by the ground? So problem number 6, so we'll just do exercise 9 here. Exercise number 9, let me get it all in. That's no big deal. I don't think students have much of a question on this thing. So the normal force is just the force it's just equal to mg. All right, because here's the deal. Earth is pulling down on this thing, on this sled, this guy on the sled, with a force of mg, and the ground is pushing back up on the sled with a force of Fn, okay, normal force. He's not being accelerated through the ground, so therefore there's no acceleration, so these forces are in balance, so therefore Fn equals mg, okay? And what else we got? Okay, if the coefficient of static friction between the snow and the movers of the sled is 0.14, how much force is required by the team of 5 dogs to move the sled? Well, they've got to overcome that frictional force, which I think we do pretty much. So basically the frictional force, the static frictional force, the max static frictional force that they have to overcome is equal to mu of k, mu of s, which in this case mu of s is equal to 0.14, times mg. So there you go. All right, I'm kind of sailing through this stuff because, all right, now once the sled is moving, the force required to move the sled drops to 250 newtons. So now we've got the kinetic, determine the coefficient of kinetic friction. So this is kind of a fun little problem. It's taking it a little bit different. So on question number 8, we go, oh, okay, the kinetic frictional force is equal to 250 newtons. Now, some of you that have taken me for 210 and are just kind of taking this class just for fun or to whatever, I mean, you're welcome, and it's to be here, and it's great that you're there, but might be going, well, wait a minute, you always taught us the kinetic frictional force was taking energy out of the system, so therefore it's negative. Well, in this case, we're just going to work with the magnitudes of the forces, and that will equal mu of k times mg, which again, you just found the answer. So the answer to 8, f of k, is just, so mu of k is equal to 250 newtons divided by mg. Now, be careful. If you're not used to doing these things, just carry which is the answer to 6. Okay? All right. I'm going to have to break this one into two because it goes. So looking at slide 36 in the drag formula, we did this before. Now, if a bicyclist, so if you look at slide 36, how much more force must he apply to overcome the air resistance? This question is messing with people, all right? Because they're like, how much more force must he apply? How many times? What's the magnitude? I should probably add that. How many times? What is, how much more? 4 times. It comes out to be 4 times. I'll just tell you, okay? It just comes out to be 4 times because the drag for a bicycle is the coefficient, this, whatever slide 36 says, I can't remember exactly, but it's got a v squared times f, or times the wind speed, v squared times something else that gives us the drag, and I can't remember what it all is. That it? But anyway, so if 2 v is equal to 2, then v squared is equal to 4. So so if I double 2, now if I make v equal to 4, then v squared is equal to 16, so I need 16 times more force. So it was poorly worded. I can see why. I got a question from a student who I know really well, and it's like, why is she having issues with this? I see why now. It wasn't worded very well. All right. Okay, this is all from notes and everything else. All right, curling rocks. Let's talk about curling here. Okay, So put that aside. Let's talk about curling. Okay. If in the video, now this is completely, these numbers are so wrong. I gave my actual 210 students on their exam a much better, I'm sorry, I was looking at something, a much more realistic thing. They do not release that stone at 7 meters per second. They release it at around 2 meters per second. And the coefficient of kinetic friction is like 0.02. I mean, it's really, really low. So this isn't very good. What's the force of kinetic friction the ice puts on the stone? Once again, this is just like the dog musher, so this shouldn't be too bad. Okay, if the stone releases point at a speed of 7 meters per second, how many meters would the stone travel before coming to a stop? So on 15, we look at it this way, remember? So 14 is pretty straightforward. 14, mu of k is given, 0.168. I think I looked up the coefficient of static friction between skates and ice or something like that, or ice on ice. But it's real, those curling stones and the type of ice that it is, really, really low. Don't forget the mg. So it's 19 times 9.8. So the kinetic frictional force is 0.168 times 19 times mg times 9.8. Okay, so you get all that. Then 15, f of k times the distance is equal to 1/2 mv final squared minus 1/2 v naught squared. Okay, since f of k is negative, we'll just won't worry about it. So this is, and v naught squared is equal to 0. So you got minus f of k times d is equal to minus 1/2 m times 7 squared. The negatives cancel, so f of k is equal to 1/2 mv naught squared, your kinetic energy divided by the distance. Your initial kinetic energy divided by the distance, because your final kinetic energy is 0. All right? Okay. Smarter every day, curling stones, those are things I expect you to do from the... What is the weight of a baseball? All right, so you know how to do this. Weight is equal to mg. Convert the diameter, d equals... This is the diameter of a baseball, 6.71 centimeters. How many meters is that? Okay, 0.0671. Now, calculate the density of the baseball. Hold on. So here's where we're having issues. Okay, here's where we're having issues. Problem 20 and 21. The baseball will float. But look, you've got to convert diameters. I forgot to tell you to convert it to find out what the radius is. So for problem 20, you got to do this. You know that the mass of the baseball is 0.145 kilograms. You know that the density is equal to the mass over the volume. Volume is equal to 4/3 pi r cubed. Okay? R is equal to 0.0671 divided by 2, which is equal to 0.03355. I think. Let me see. 0.0671 divided by 2. Yeah. It's 0.0355. So you got to put, so to find the volume, you got to go 4 divided by 3, put all that in parentheses, times pi, or you could do 3.14 if you wanted to, and then 0.03355 times 0.03355 times 0.03355. Put all of that. This will give you some answer. And then your density will equal 0.145 divided by that answer. That's been kicking people's butt. Because I think they forgot to take the radius is equal to the diameter divided by 2. All right? And I think I was being sneaky. I did that on purpose. Okay, so once again, I think I think this is all worked out in the other video. I think you can work it out nicely. Convert it to pounds. So you add the weight of the ball. So you take density to 1000 G times the depth. So that's 3130. So no one's having trouble with these, I don't think. Yeah. All right. So the buoyant force, which is kind of a cool thing too. When you convert the buoyant force in newtons to pounds, just go newtons to pounds on Google. It'll look like this. Like say I've got 35 newtons to pounds. 35. Here's a table I've never seen before. 35 convert. There it is. Okay, so you can do that kind of stuff. All right, I think I really walked through this in the lecture videos. If you actually go through it, and this time I give you the radius, so it's not too bad. So you can find the volume of the ball, which again is 4/3 pi r cubed. Okay, so for problem 23, it's the volume is 4/3 pi r cubed. And I've already shown you how to work that out. Okay, and so the buoyant force that you're going to get will equal 1000 times the volume times g. Okay, that'll be the buoyant force. That's how much force is pushing up, and you've got to push down. Okay, now the way the ball is going to help you a little bit, mg of the ball is going to help you a little bit. So the force that you're going to need, that you'll need to push on the ball is equal to the buoyant force minus mg. Okay, minus the weight of the ball. I think they give you the ball in kilograms. Okay, so that's how you solve those 3 or 4 questions to that. Okay, all right, out here.